Hello future physicists, welcome. Today we are absolutely mastering work, energy, and power. You know, if you're gearing up for your WAEC, JAMB, or NECO exams, this is the explainer you've been waiting for to really nail those tough questions. So here's the plan. In just the next few minutes, we're going to build up your physics toolkit, packing it with all the core concepts and essential formulas. And then we're putting that toolkit to the ultimate test against some real actual past exam questions. Sound good? Let's jump right in. Alright, first up in our physicist toolkit, let's talk about the fundamental concept of work. Now, this is absolutely crucial. In the world of physics, work has a very specific meaning. Work is only done when a force actually makes something move. I mean, if there's no movement, no displacement, then no work is done. It's that simple. And that little theta in the formula, don't let it scare you. It's just the angle between where the force is pushing and where the object is actually going. Okay, check this out. Here is a quick win for your exams. When the force and the movement are lined up perfectly, going in the exact same direction, that angle is 0. And the cosine of 0 is just 1. So you can forget about the cosine part and simply multiply the force by the distance. In this case, 50 newtons times 10 meters, that gives us 500 joules. See? Easy peasy. Right, let's grab the second tool for our kit. Energy. I want you to think of energy as the fuel for work. You literally can't do any work unless you have some energy to spend. Now let's break down the two main types you're definitely going to see. So here they are, the two big players in mechanical energy. On one side, you have kinetic energy. That's the energy of motion, you know, like a car speeding down the road. On the other, you've got potential energy, which is all about stored energy, like a rock perched on the edge of a cliff just waiting to fall. And you have got to remember these two formulas, 1/2 mv squared for kinetic and mgh for potential. Okay, listen up, because this is one of the most important fundamental rules in all of physics. The total amount of energy inside a closed system never ever changes. It's always constant. It just, well, it changes its outfit, you know, shifting from potential to kinetic or maybe turning into heat or sound, but the total amount is always the same. Let's actually see this law in action. Imagine this. At the very top, the object is holding all its energy as potential energy. But as it starts to fall, that potential energy begins transforming, converting into kinetic energy. And right at that split second before it hits the ground, boom, all of that stored potential energy has become energy of motion. The grand total, 200 joules, hasn't changed at all. Okay, time for our final tool for the kit. And that's power. See, power isn't just about how much work you're doing. It's about how fast you're doing it. It's all about the rate of that energy transfer. Let's look at an example. The work done here is 500 joules, right? But because it took 10 seconds to do it, the power is 50 watts. Now, what if a more powerful engine did that same 500 joules of work, but did it in just 5 seconds? Well, it would have a power of 100 watts. It's all about the speed. Alright, our toolkit is officially assembled. It is time for the real test. Welcome to the gauntlet, where we are going to put our skills to the test and tackle some past exam questions. Let's do this. First up, we've got a question from a recent WAEC paper. Okay, let's break it down. We have an electron, we have a voltage, and they want us to find its kinetic energy. So the big question is, how do we connect these pieces of the puzzle? The secret here, the real key, is realizing that the work done on the electron by the electric field is what gets converted into its kinetic energy. And the formula for that work is the charge of the electron, E, multiplied by the voltage, V. So we just plug in the numbers, but, and this is important, we have to remember to convert 30 kilovolts into 30,000 volts. Do that, and you get your answer. And yes, that brings us to a classic exam trap. Oh, the examiners love this. They love to hide little prefixes like kilo, milli, or micro in the question. You have to always convert everything to standard units before you start punching numbers into your calculator. If you don't, you're just throwing away easy marks. Next up, a JAMB question. And this one is a perfect test of the law of conservation of energy. They want the total energy at the very end. So what does our big physics rule tell us about that? Okay, think about it. Since energy is conserved, and we get to ignore air resistance, the total energy at the very beginning is exactly the same as the total energy at the very end. So why do all the hard work of figuring out the final energy? Let's just calculate the initial energy. The ball has kinetic energy, because it's moving, right? And it has potential energy because it's starting up high on a tower. We just add those two together, and that's our answer. 15 joules. The total energy never changes. Now here's exactly where students can slip up. It's so easy to do. They calculate that initial kinetic energy perfectly, but then they completely forget that the ball's already 10 meters up in the air. That height gives it potential energy right from the get-go. You've got to account for both to find the total. Alright, for our final problem, we've got a NECO question involving an explosion. This is a classic scenario, and it's designed to test two really important principles: the conservation of momentum, and of course, kinetic energy. Let's break it down piece by piece. First things first, we have to use the principle of conservation of momentum. Think about it. Before the explosion, the bomb was just sitting there, at rest. Its initial momentum was 0. That means, after the explosion, the total momentum of all the flying pieces has to still add up to 0. This lets us set up an equation and solve for that unknown velocity, v. Once we've got v, the second part is actually pretty straightforward. We just calculate the kinetic energy for each of the two pieces separately, and then add them up. Be careful, though. There are two big traps here. First, messing up the signs. You have to remember that momentum is a vector, which means direction matters. If one piece is flying in a positive direction, the one going the opposite way must have a negative velocity. The other trap. Simple math errors with the mass split. Just take a breath, and double-check your numbers before you move on. Phew, we made it through the gauntlet. You did great. Now, let's pull all this knowledge together into your master plan for exam day. Okay, look at this. This right here is your core cheat sheet. These 4 formulas are the absolute key to solving almost any problem on this topic they can throw at you. Seriously. Pause the screen, take a screenshot, write them down on a note card, whatever you have to do to commit these to memory. And to finish up, here are some final pro tips. Don't lose easy marks just by forgetting your units. Always check which value of G the question tells you to use. Keep your eyes peeled for those tricky questions. And most important of all, practice, and then practice some more. Especially those conservation problems. They are pretty much a guaranteed feature on your exams. So there you have it. That's your complete toolkit. You've got the formulas, you've seen the common mistakes, you know the methods. The only real question left is the one that's going to be on your exam paper. And when you see it, just remember, every single problem is just a puzzle about energy changing its form. If you can master that one idea, you're going to master the test. Now go get them. Good luck.